Good morning, everyone, and thanks for the, again, excellent turnout. And welcome to Neil Phillips, who's going to give the final lecture in the gold series that he and his colleagues at Stellenbosch have very kindly put together. And I must say it's been excellent. And of course, I should add Julian Burncombe there as well. So I would just like to briefly again introduce Neil. He graduated in geoscience from the University of Melbourne, completed his BSc honours and then a PhD at Monash University, and then did an advanced management program at Harvard Business School. He co-founded the Archean Gold Group at the University of Western Australia in 1980 with David Groves, and they developed the geological principles which are still used widely in gold exploration today. He had a period at the University of the Witwatersrand from 84 to 87, led about 40 projects on operating gold mines, and then maintained these projects as a professor of economic geology at James Cook University and chief of the Division of Exploration and Mining at CSIRO. He has an honorary professorial appointment at Stellenbosch University, University of Melbourne, and Monash, where he continues to do ongoing research and collaborates and teaches gold geology and does work on his other love, which is granites. In 1995, he founded the Geology of Gold course and still contributes to this annually. He's also been editor of Applied Earth Science, the Applied Earth Science Journal, and the AusIMM Australian Ore Deposits Monograph. He regularly publishes in scientific journals, has written and edited several books, and Beyond Gold Research with Julian Burncombe, and he has a keen interest in the Stellenbosch Barberton Gold team. He also has ongoing collaboration with John Clemens and Alex Kisters at Stellenbosch University on granites and gold, obviously. So welcome, Neil, and we look forward to your wrap-up of the talk of the presentation series today and your views on Wits Gold. Thanks very much.
John, thank you very much for that introduction and also for the opportunity to round off this 5 weeks of lectures during March. We've only just fitted it into March. I think that's probably good. I didn't want to do it tomorrow and be labelled as giving a talk on the Wits on April Fool's Day, but some might think that's appropriate. We'll see. There's the list of 5. We've just rounding off the last one. That's the rationale behind the whole series. I won't read through that. That's really to be picked up on YouTube if anyone wants to know what's behind the whole lot, the linking theme. And I'm really going to address alteration and the Witwatersrand goldfields today. I'm going to do that in the context of having already heard about fluids, structure, alteration around Barberton and around the other greenstone gold deposits in Australia and also of the Cupwell Craton. So I guess the key question is there any hydrothermal alteration in the Witwatersrand? How do we answer this question? What sort of material do we sample? And what tests do we do? And that's some of those questions are not all that straightforward. They need a little bit of thinking and planning beforehand. So I'm going to pick out 1 or 2 of the principles from 4 weeks ago, and you will have seen how they work with the other speakers as well. Talk a bit about shales in the Witwatersrand supergroup and finish off with some textures that are visible and can be seen as people wander around underground and looking at core. There's what we talked about earlier, a really simple view of alteration. And we might have a normal rock and it interacts with a fluid in the Earth's crust. If those two react, we're going to change the composition of the rock, so we get an altered rock. We'll call that alteration. And we're going to get a different fluid. Now, not the topic tonight, but why, today, but why we're interested in that different fluid is if it changes such that the gold is deposited, then of course we're well on our way to mineralisation. So that's why the whole issue of alteration is so important. What I'm going to do is look more at the altered rock and say, can we identify any? What's its geometry and what does it tell us about processes? Well, we look at this surface here. I think in the upper part, and I'm not sure if I can make my pointer work. It's up there, it's a blue pointer in the top middle. We're looking at some sort of sedimentary layering here. We're looking at a great patch here in the middle. We're looking at what looks like cross-bedding at an angle there. And we can interpret that and say, I think I see sand and clay laminae in the top. I see a massive sand patch, perhaps the scour surface, and then cross-bedded sand over in the centre left. Now, different people might have slightly different interpretations or more sophisticated interpretations, but there's nothing wrong with that at all. And yet what we're looking at there is cordierite and quartz. And nobody's suggesting that we've got detrital cordierite there. The quartz is making those hard ridges, and the cordierite, the intervening places, and there's pock marking all through there, which is picking out the cordierite porphyroblasts. We're looking at a cordierite biotite hornfels, and we can work out that it's formed at 500 to 600 degrees. So nothing wrong with those textures at all, nothing wrong with the sedimentary interpretation, but it's actually quite high-grade metamorphic rock. And keeping that in mind, we can look at the sample on the, underground shot on the left, and again, nothing wrong there with interpreting unconformities, cross-bedding and so forth. But that's a metamorphic rock. That's been to 300 to 400 degrees. So the two are not incompatible. And on the right-hand side, obviously that's Bankert, Central Rand, I think it's Durban Deep. And again, a lot of sedimentary features we can see there, but it's a metamorphic rock. Now we have seen this earlier, and I'll just go through what we're looking at. We can recognise these shapes that look like plagioclase laths, white, and then we can look at patches around them that look like an ophitic texture that would be clinopyroxene and plagioclase, and we can look at these patches here of opaque. And if that's our life and that's our lease or our domain of where we're doing our geology work, then that's what we see. And it's totally reasonable for that ant or geologist or whatever to interpret what they see and say, that's normal rock, that's all I see, I've walked all over my land and it's all uniform. But what's not available to that person or that ant is a bigger scale, and way down in the left-hand corner there, a lot of that same texture is visible, but completely different minerals of a completely different colour. And it's chloride giving the dark green and carbonate giving the light in the top right. And if that person, ant, talk to their neighbours, they seem to be fighting at the moment, but if they talk to their neighbours, then the neighbours might share some information and say, but down in the bottom left corner of our plot, we have something different. Maybe you should come and look at it, or it's rich in chloride. So again, it's how much is available to see often determines the picture. So on those notes, let's turn and look at the Witwatersrand. I mentioned the Kupfval Craton. Previous speakers have all talked about the Kupfval Craton and examples from there. Looking at some of them, we had Alex and Caitlin talking about Barberton, Julian talking about Murchison and the other greenstone belts around the north and to the west. Archean greenstone belts. I'm not going to talk about those any further, but I am going to talk about the Archean Witwatersrand basin here. P for Pretoria, J for Johannesburg. It's about 300 kilometres long axis there. A lot of it's not outcropping. There's good outcrop around the Vredefort Dome. We've got Johannesburg here, and 100 kilometres or more out to the east, we've got Evander, no outcrop. East Rand, not much outcrop. Central Rand, West Rand, Carltonville, Klerksdorp and Velcom. So we've got quite good outcrop through the Central Rand, and that's where George Harrison first found gold at Lunglukta. And it was a very, very quick progression heading east and heading west to identify that that main reef package continued, and wasn't too hard to trace that undercover and find the East Rand. And so that was mined out fairly early. Some of these discoveries like Evander, Carltonville and Velcom really are world-class. And I mean, not just the fact they found an awful lot of gold, but the way people went around Carltonville in a fairly depressed era and what they did scientifically and the risks they took, I still find it mind-boggling. It's just a wonderful story. So that's a fairly large area of 300 kilometres by 100 with lots of gold mines and goldfields. And I'd like to mention some collaborators there that have played special parts in this work. Jonathan Law and Russell Myers, Spike McCarthy, Judy Palmer, Zolly Ramos, Gina Dong and Dr. Joe on the mineralogy, Roger Powell, and many other colleagues and students to whom I say thank you very much. Because what that's allowed us to do, and John in his introduction alluded to this, is to cover quite a lot of the mines rather than, and this is back to the ant seeing just one little bit or trying to see the whole big picture. We've been able to do underground work on all the mines there that are labelled, collect samples, look at drill core and some surface material where appropriate. So we've got the mines here at Evander, the 4 of those. Not much coverage here in the East Rand for the reason I said that this was discovered early and mined out fairly early. So 3 or 4 mines there only. Not a great deal through the Central Rand, but there are some. And then pretty good coverage from the West Rand down through Carltonville, Clarkstorp and Velcom. But the chance there to see the bigger picture as well as the detail that one would see underground on each of those mines. But what do you look for? Well, if we ideally walked into the Witwatersrand basin before having done any work there, I might ask the question, can you show me some basalts and can you show me some shales? Because they might be useful for my alteration and metamorphic studies. And the reason behind that is basalts and shales are made up of a large number of essential major elements. You don't have basalts that really lack any of those: silica, titanium, aluminium, iron, magnesium, calcium, and sodium. And shales are much the same, slightly different mix, but a significant number of major elements, and therefore a significant number of minerals are likely, and therefore a significant amount of information can be gleaned. Contrast that with clean sandstones, where you've got silica, and if they're heated to 200, they're quartz, and 400, they're quartz, and 1500, they're quartz. And eventually at 2000, they might melt. So not very helpful for telling us a great deal about the later history of those rocks. There's our 7-kilometre Wits supergroup, and it's starting to throw up some of the difficulties. It's nice saying I want to look at the basalts and the shales, but you look at that column there and say, well, I don't actually see much in the way of basalts there, perhaps the crown lava, but also keep in mind where the gold is. The gold is in the upper third there, and that's going to be where there is underground access, and that's going to be where there's a lot more drilling. So the crown lava might not be quite the thing. There's another bird lava further up, but basalts are a little bit tricky to get enough to get good coverage. The shales actually are a little tricky too, because a lot of them in the lower bits is where we find them in outcrops, sure, but we really like them in mines, and there's not a great deal that's accessible. In that upper Central Rand group, there's obviously the Boyson Shale, but there are a number of other ones there, the Jeppy just below that, and a series of other shales, fairly small, but in each of the goldfields, we can normally find 1, 2, or 3 horizons mixed in with the reef packages and work on those. I'm going to pick out one of those and look at it in a bit more detail. As far as alteration and elements go, of the major elements, a good starting point is to say, well, silica is going to move. We know it moves. It forms quartz veins in all sorts of environments. And potassium and sodium are going to move because they're +1, left-hand column, and large, low charge. So they'll move in and out in all sorts of fluids, in the Earth's crust. The divalent, iron, magnesium, calcium, a little bit in between. They'll move in some environments, less so in others. But the ones that are really going to stick around and not go into solution are the +3 Al, aluminium, and the +4 titanium. So those will be a good target first to look for immobile elements that might help us see through any alteration event. That was only the majors. There's quite a lot of minor elements you can also use as well that are high charge, don't move much, and will let us look through any alteration event. Aluminium, titanium then, and we're going to pick out niobium as well. And to keeping it simple, we'll stick with niobium, aluminium, and titanium, NAT, and we can work on those. We could work on other ones. Sometimes they're not analysed. Today, I know we can analyse 50 elements or more just like that, but we've got to use older analyses as well, and you have to be a bit realistic in what's available and what isn't. I really like this diagram. I think it's recognisable that's Africa. You can see my pointer's not going to work over there, but the Niger River in the west, the Nile River, obviously, I guess that's the Zambezi, Limpopo, Okavango. We've got the Congo River here, the world's second biggest river, as far as volume is concerned, and the world's deepest. And we've got the orange. And I'm going to talk a little bit about the orange. I hope I'm not going to tread on any diamond feet when I do so. A little bit about the orange. It drains a large part of South Africa, catchment of about 1 million square kilometres, 2,000 kilometres long. So think down at the end of the orange, what's going through there out into the Atlantic Ocean? And the answer is a sort of averaging of what the rock types are through its catchment in South Africa, and also a reflection of the climate there. And that same would apply to the Congo, where a very different climate that's wet and tropical and deep weathering and so forth, it'll be quite different from the somewhat arid environment of the orange. Let's go and look and see what comes out. I've never been here, but these are nice photos. Don was actually talking earlier today about the steeper margins for the orange. I just chose this and sort of asked the question, what sort of rocks would you find forming today at the base of this scarp? And the answer is conglomerates and breccias that have rolled down from straight up above. And if we had ultramafics here, we'd get ultramafic rich conglomerate, and it could vary to granites there and sandstone or something else over there. But the point being, the conglomerates and breccias can be highly varied over short distances. Moving to finer grained, the sands, and this is obviously sand because the four-wheel drive hasn't bogged somewhere near the mouth, and the sands in the bottom left being brought down. We know a lot about those in the Witwatersrand, about sands, the bars, and what happens there in flow directions. But what I want to look at more is here in the middle, the mouth where these rivers enter the sea, and you'll be able to see a large plume, and that plume is clay. Now, we don't know straight away at the moment what that clay is, but you can see this clay plume here, and it's heading out tens of kilometres and even hundreds of kilometres into the Atlantic Ocean. Now, the clay in that could be chloride, it could be illite, it could be smectite, or it could be kaolinite. We don't necessarily know. But the thing is, whatever comes through here and enters the ocean is going to be a mix. And it's going to be a fairly homogeneous mix representing the major part of South Africa and the climate. And we're not expecting any sort of sorting out here. So we're going to get a clay type dominating out here. And it's going to be consistent over many kilometres, tens of kilometres. Now, this is the Congo. We've gone 2,500 kilometres north. The climate's changed. The river is obviously much bigger, and this plume goes 100 kilometres out into the Atlantic. And this is a major source of iron for the South Atlantic. But again, the same point applies. We may not know exactly what clay this is, but whatever the clay or clay mix is, it's going to be uniform. We're not going to find a situation here where all the chloride clays go left, kaolinite clays go right, and the illite clays go straight ahead. It's not It's not going to work like that. This is an averaging of large part of the continent coming out through the mouth of the Congo on the Angola border. Now that's important because the bit that comes out of that is looking at shales is particularly good because we don't expect them to vary over short distances. We actually expect them to be very uniform over distances laterally. And of course that has been proven over and over again in different parts of the world, particularly in the oil field type situation, say the North Sea. Looking at the top left here, we're going to now apply this to the Wits. Johannesburg's there in the central Rand, East Rand's on the right. We're going to look at this West Rand area of Doornkop, Cook and Western areas. Here is a very simple reef package, unconformity, carbon matte sometimes, conglomerate, quartzite, and the shale. And that's the shale that we're interested in. And there's several of those in different goldfields at different heights. But we're going to look at one in those three mines I mentioned. Now, that shale over in this strat column doesn't show up because it's only a metre or so, a few metres thick. But it's in this position in the upper Wits, in the Kimberley package, where people have accessed to mine things like the Kimberley reefs. And you can see the sampling here. There's sampling here from drill core. There's sampling here, all just represented as a circle, from underground. And so it's a mix, and it's covering 20 or 30 kilometres. And it's pretty easy with so much drilling in an area like this to be confident that we're looking at the one horizon. So we're looking at the one shale. It should be very uniform over that type of distance. But what we actually find, we're still getting a series of contradictions here because we're finding pyrophyllite, muscovite, chloride, quartz. Well, first of all, they're not usual things in shales around the world. But secondly, we're getting rocks like this, and that's chloritoid, these little blades, rocks like this that are all pyrophyllite. And you say, how does this fit if that is a uniform shale over 20 or 30 kilometres in the West Rand? So we're going to come back to that. We've got a valuable mineral assemblage here, and we're going to pull it apart with some geochemistry. And we're going to use NAT, niobium, aluminium, and titanium. Well, those three are immobile, so they will look back to when that clay formed. They both vary in amounts, the titanium and the niobium, but they vary with one another. There's a constant ratio, straight line through the origin. And the same with titanium and aluminium, straight line through the origin, and put those together. And we've got a constant ratio between titanium, niobium, and aluminium, very much supporting what we'd predict from looking at the mouth of the Orange and the Congo, that we're looking at one clay type here. We're not seeing any signs of variation from the immobile elements. But that's quite contradictory to finding chloritoid in patches, pyrophyllite in patches, chlorite in patches, and saying what's going on here. And there's not even a system to where those occur spatially, not on the scale of that 30 kilometres. This might help to understand a little better. We've got aluminium up here. We said we're using that as immobile. We've got iron and magnesium in the bottom left, and we've got potassium over here. These are our samples from that K8 shale. I've also chucked in about 5 extra from a possibly similar horizon of Velcom. So it's a long way away. We won't worry too much about those, but they are roughly the same. Chloride clay would be down here, illite clay with the potassium over here, and kaolinite up towards that corner. What we're seeing there in the K8 shale, if you want to interpret it in terms of different clay types at the start, we're looking at more variation than you get in probably half the Atlantic Ocean. That's the sort of variation from chlorite to kaolinite you get from perhaps the Falkland Islands up to the Caribbean. You just don't get changes like that because the oceans and the big rivers coming in are mixing and giving you a homogeneous clay heading offshore. It does vary over thousands of kilometres, but it won't be varying over the 20 kilometres that we were dealing with. Now, what we're looking at there and those big changes don't look like weathering. It's a good question to ask, but what we're looking at there is a, have a look back here. We're looking at perhaps down here, starting around chloride, the least altered ones, and we're looking at a change here to addition of potassium. So we're looking at addition of potassium out towards illite here, which would be perhaps muscovite, and we're also looking at a massive loss of iron and magnesium to get up there. It doesn't match weathering, and anyone who wants to follow that up, it's well worth reading Judy Palmer's work of the late 1980s. It's published in 2 or 3 places. Spike McCarthy's an author, as am I, and note that the geometry and the geochemistry doesn't fit. So it's good to ask the question, but we won't head down that path. Now, same information, and we're overlaying some metamorphic minerals. And this is where the power of sorting out how these form then lets us use them right around the basin. Least altered chloride clay here in, excuse me, in a shale. Chloritoid here, muscovite and pyrophyllite. So you can see that we had the one original starting material based on our niobium, aluminium, titanium. We had dramatic changes involving loss of FeMg, driving us right up to the top, and we had some increases of potassium. And so the way to get compositions that will stabilise chloritoid is through some alteration, and same with pyrophyllite. The way to get pyrophyllite in those K8 shales is to have considerable alteration, and you need to lose virtually all the FeMg. And that's why you start getting these pyrophyllite, muscovite, chloritoid, chlorite assemblages. And they're highly varied, but from one place to another, even within that 20 kilometres, 30 kilometres. Now, here's where you can use it to map alteration out in the whole basin. And what we're looking at is the arc there of Evander, East Rand, Central Rand, West Rand, Carltonville, Clarkstor, and Felcombe. And from all the mine work that I related to earlier, you can see that it's common to find pyrophyllite at Evander, a bit limited in the East Rand. That's because of access. It's there on the Central Rand, and it's there in virtually all the mines as you come around there. And I should point out, these are places where we've been able to confirm pyrophyllite from our own work. It involves X-ray diffraction and, of course, sampling and knowing what you're doing underground. I wouldn't normally separate out pyrophyllite and chloritoid to be thinking of them as coexisting assemblage, but I want to do that here and look at the chloritoid. And you see, again, a lot of chloritoid at the mines right around the basin, not so much in the East Rand because of the lack of access, but if you look at the old reports, they even map a thing called and write up a thing called the chloritoid shale. So it's obviously been known for quite a while and known in some of the mines that are closed. We haven't recorded it there, but one could. Obviously, the importance of it wasn't noted at the time. Okay, so we're going to flatten out that arc like this with Evander on the left, East, Central and West Rand, Carltonville, Clarkstor and Felcombe. Down along the bottom here, we've got that main reef position where a large amount of gold has been produced. We've got a Kimberley reef position here. We've got this Vaal reef, basal reef section down here, and we've got VCR that's producing gold, particularly, say, Carltonville, West Rand. So we've got our major producing horizons there. Now I'm going to straighten that out a bit to make the Boyson Shale, a pretty well-known marker in the middle of the Central Rand group, make that just flat. And you can see here, looking at the brown colours, we've got these huge tongues of pyrophyllite, chloritoid, pyrite rocks. So these are shales predominantly, but large tongues of tens to hundreds of kilometres. And we see here coinciding with that Kimberley type position, the VCR position, the basal reef, Vaal reef type positions. So we're getting this on a very big scale, covering not just a mine and not even just a single goldfield. So there's no possibility that well, using an example of someone tonight, there's no possibility you could sit at Kloof just here and see the bigger picture. It's simply not possible. And it's not even possible to go next door to Lebanon and Fentis Post and see the picture. It's on a much bigger scale than that. And this is not work we've done. This is work by Barnacote, the Leeds University people, and Anglo. And what they've done is done a section at right angles to that arc. So it's into the basin. And you can see, again, these great big tongues of brown colours, and they're pyrophyllite chloritoid type rocks we'd interpret as alteration, and they're coinciding with the reef packages. We'd have Kimberley type package and main reef, bird reef type packages. And then you look at the scale of the mine workings there, a few hundred metres vertically, would cover a lot of the working reefs and a few tens of kilometres horizontally. This is a stretched diagram. And again, you could work all day, all week, all year, all career, and not necessarily get out of that. So it'd be quite valid to turn around and say, there's nothing special about that. That is the rocks you get at this mine. They're all the same. They've all got pyrophyllite chloritoid. And perhaps the bigger picture is, well, no, those minerals are not common in shales worldwide. They might be common where you are. Now, having worked like that on the K8 shale, or on some of the other shales I alluded to in different goldfields and at slightly different positions in the Central Rand group, one turns up and says to the exploration manager, I think I've found some alteration, at which the manager says, of course, how exciting, this might lead us to a new discovery. And I hark back here to particularly Julian's talks on integrating this with structure and so forth in greenstone belts, and the success this parameter has brought in discoveries, say, in the Yilgarn Craton. And the manager might go on to say, well, we now have a target twice the size or more than twice the size when we're doing our exploration. Now, that was just one shale. I won't go through the others, but some of those other ones are published, and it gives you a feeling for the vertical as well as the lateral extent of these alteration as recorded by the shales. I want to look at some chloride balls and a little bit at quartzites, and they're not really quartzites, they're actually arcoses. These are quartz pebbles. It's a conglomerate. It's from Beatrix Mine at the south end of the Velcombe goldfield. We've got round shapes here, and a lot of this is pyrite. But what we're interested in here are these dark green balls, and there's about 15 or 20 of them through here and another dozen up in this patch. And we know they're chloride. And you look at that and say, well, what are those doing? Now, what we do know about chloride is it's really soft, and it's not going to be transported in a conglomerate more than about 1/2 metre before it gets crushed. So it didn't come into the basin rolling along with some form of iron and with these quartz pebbles. So what's it doing? We'll cut a thin section and have a look at one. And there it is, filling up most of the field of view. You can see little bits of quartz down in the bottom right. First, notice the shape. It's a pretty distinctive shape there. And we might think, oh, that looks like a bit like a garnet. Have a look inside, and a lot of that dark material is chloride, but it's also white mica. And that white mica is pyrophyllite and margarite. And margarite is calcium white mica. And I think this is the first record of margarite in the Witwatersrand. And one has to ask, well, what's that doing there? And there is a really neat explanation that comes out on why we've got a little bit of margarite in the chloride balls. Now, if those chloride balls were garnet, which the shape suggests, then garnet represented here by almandine, has got FeMg and it's got Al. It's got no potassium. And chloride's like that too. It's FeMgAl and no potassium. Garnet also has a calcium component, the crustal component, and probably not much of that. It's subordinate to iron and magnesium, I would guess, and that will be attributed to the margarite. So here we're getting roughly the same compositions. You add a bit of water, you get chloride, and you convert that to mostly chloride, a little bit of porphyry to balance the Al, and you've also got a little bit of calcium as margarite. And so how we'd interpret that as the chloride balls have come into the basin as garnets and they've been changed to chloride, but still kept their shape. It answers another unexpected question. Well, the question's not unexpected. It's unexpected that we got that answer. And that question is from Julian's work last week and mentions of Consort by Alex and Caitlin, we know we've got garnets in the greenstone belts. Now, garnets are very resistant to beating up or smashing or those type of things. They're very good detrital component, plus their high density means they'd be a high candidate to come here. But you don't find them much in the Witwatersrand reefs, despite having greenstone belts in likely source areas. So we've answered two questions. What are the chloride balls? Well, they used to be garnets. And where are the garnets that should have rolled into the Wits? Well, here they are, and they changed after burial. Jonathan Law provided these four. We can see in the top centre here a grain of quartz, and down here some feldspar, more feldspar on the right, and more feldspar over in the bottom left. And it's pretty fresh. And the next step in the same set of core, we're looking at a big feldspar in the middle there, and you can see it's altered to quite a lot of white mica, but it's still recognisable as feldspar. And the quartz there, much the same, a little bit ragged. Take that stage further, and we're now looking at over here quartz, but it's very much got ragged edges, and it's sitting in a sea of white mica, and that white mica is porphyrite and muscovite, with little books of white mica here. The quartz has lost its round shape quite decidedly. And fourth stage, what we're looking at here is you can still see the quartz, 2 grains there. Absolutely no suggestion of being round or anything like that. They're quite ragged. A strong fabric defined by the white micas running roughly east-west across here. Big books of mica, and so it's a porphyry, muscovite, quartz rock. Now, very reasonable to call this a schist or a shale, because that's what the mineralogy is, and yet this is an altered arkose. And it shows the difficulty of mapping these things in isolation without thinking of what these things might have been and realising they're in high strain zones at the moment. So it's a high strain zone. A lot of the original texture for this photo, the original texture has been destroyed, and rather than map it as a shale drape, we should possibly be thinking of a highly altered rock of some sort. Just one of these. This is a chert pebble. You can see a bit of layering in it. It's mostly silica, a little bit of iron. And there's been replacement of that iron by addition of sulfur to give pyrite around the edges and on some of those sort of bedding plane cracks. These are actually quite widespread, and they occur in patches. You can go for days or mines without seeing them. And then in this case, out at Crutflay on the Witwatersrand, there's a whole lot of it. A really nice little story there. And Ramdor saw these things. I mean, this is more than 50 years ago. He's reported the pyrite, which we're looking at, with this Widmanstätten structure of X solution in a titanemagnetite. And then Russell Myers also recorded the same sort of things there. The yellow is pyrite. The bluey grey is not pyrite. That's more the titanium phase that is exsolved and has not undergone this change to pyrite. So he's picking up these igneous titanemagnetites, at least that's what they're interpreted as, and seen them pyritized after burial in the basin. And then Russell also sort of collected the chocolate-coloured pebbles out the back of Clarkstorp on the surface today, and then collected these pebbles from underground in the Witwatersrand reef and sort of said, don't they look similar? A little bit of a teaser, that one, and this is certainly a teaser too, and perhaps slightly frivolous, but we might look at this and say Moody's Group, Barberton, arenaceous rocks, and this would be the type of thing perhaps that Caitlin and Alex were talking about as channelways for lots of fluid and a higher strain zone. But we can also turn that around and look at it this way. Still got our arenaceous rocks, it's the same photo, and across the horizontal here, high strain zone, and this is actually carbon leader. So it's carbon leader from Carltonville, and it just reminds us that we can have lots of different orientations for these channels that fluids use, and something like this, it's not going to be horizontal, it's going to dip in the dip away from us. Okay, I'm going to wind up and finish with our friend and say goodnight to our ammonite, our pyrite ammonite from the museum. And remember, he floated around the Mesozoic ocean as an ammonite, died and fell to the bottom of the ocean, and then sometime after burial was converted to pyrite, which is what he is today, in a low strain but high alteration environment. So we can still see the textures beautifully, but he's undergone massive changes. So those the strain and alteration very much can be quite independent of one another. So I'll finish there. I will just flick through these so they get picked up on the YouTube. And this is where those figures and the stories are drawn from and the data. These publications. If anyone has trouble finding one, don't hesitate to call me and I'll send a PDF if I can. And finally, I would hope that formation of gold deposits will be out later this year. So on that note, I'll hand over to John in a moment, but I'd just like to take the opportunity to say thank you to Nolene, to John and to Henny for all the work they do putting this together between weeks and also during the evening to make it easier for the speakers. And also what a pleasure it has been to work with Caitlin, Alex and Julian as we've tried to make this work and integrate our different ideas and just have quite a lot of fun together. So thank you guys. All yours, John.
Thanks, Neil. Excellent stuff. And I'd just like to, respond by saying it's been a great pleasure to work with you guys. And I say that on behalf of myself, obviously, and Henny and Nolene. And, hopefully we'll do more of this in the future. But it's been a great program, extremely professional. The quality of all your presentations have been wonderful. And you've set a really good benchmark. So, let's keep it going. All right, questions and answers. Who wants to kick off? I'm very glad you touched on the Orange River because obviously it's another really important economic conduit for our diamonds that ended up on the West Coast. And fascinating there too, Neil, how you can trace the geology of where those diamonds actually came from, and the sort of country rock that they were intruded through. And there's been a lot of really good work done on the clasts, for example, that turn up on right down the lower end of the Orange River and on the West Coast. And then it tells you a fascinating story as well about those amazing diamond deposits.
Maybe that's a good lead in for your series.
Yeah, no, it's fantastic. I'm glad you touched on it. Yeah, and I guess again, it goes back. I mean, I think as you've demonstrated this amazing, solution activity. Obviously, the sharing. I see you didn't say much about the carbon. Maybe you want to comment on that. How and most of all, this amazing Karpval craton and all its superbly or superb anomalies, be it the Wits or the bushveld or diamond deposits, like, you know, the world's biggest placer are the diamond deposits on the west coast of South Africa and Namibia. It's an absolute jewel box.
Yeah, no, it really is. And I have to restrict myself a lot today to just a little bit of the bits. But there's a lot more than we could take that all further. Do you, as a matter of fact, know much about the clay types that go out the Orange River?
Again, there's quite a lot of work. One of the big discussions that's still on the go, and maybe Bill can comment. I don't see Mike on the presentation, but also the role that and I'm digressing a bit, the Carboniferous glaciers played in, you know, the Dwight-Tillite period, played in transporting diamonds, not necessarily concentrating them. And I'm not a clay expert, but there has been quite a lot of clay work done, you know, on those deposits. Obviously, when they reworked in the sea, as you'll know, the clays don't survive that well, but certainly in the land deposits, there's some interesting clay deposits as well. Yeah. Gordon, you've got
Gordon Cole has his hand up.
Yeah, thank you, Julian. Please, I've just got old and just in the last few minutes. Thank you, Neil. Just a comment on chloritoid and the East Rand. When we did a little bit of a study some many years ago now on the tailings facilities, we found quite a lot of chloritoid on the tailings facilities. So although you haven't had the access underground, it was there. The real question I have, Neil, is the maturity or the degree of alteration. Can it go too far, and what would indicate that? In other words, if you look at the alteration, if you look at the completeness of the chemical index of alteration, for example, it seems to tail off up when you get close to 1. You know, you have you seem to have gold associated with the very high values of the CIA, except when you get up to about 9.97, and then it tails off again, almost symmetrically.
Yeah, okay. The CIA is an alteration index. It's very useful and convenient, and I know you and Jonathan Law and other people, and I've sort of worked with that. It's a good sort of first pass, but I wouldn't be taking it too. I wouldn't be taking it too far, because it's really only 1 or 2 dimensions in a 7 or 8 dimensional set of major elements. So quite a bit can get lost in other dimensions apart from that XY plot. I don't know what to make of the bit from 97% to 100. I'd have to look at it, but as far as degree of alteration in the minerals, and of course the two are related, people look at these rocks and say, oh, they're all gone to pyrophyllite. My understanding always was that there was always some muscovite there too. So you might have converted things over to mostly pyrophyllite, but you always had some muscovite. So therefore you got to the muscovite pyrophyllite boundary, but you didn't go to really acid, just pyrophyllite compositions. A little hard to explain that on without a phase diagram, which I've avoided using, but yeah, the coexistence of muscovite there does tell us something, that it hasn't gone to extreme conditions. It's gone a long way because of a lot of fluid, but it hasn't gone to super acid conditions, which some people have tended to suggest.
Well, thank you very much.
George Henry is asking a question there as well, the same question as John.
Yeah, George, your question was about carbon leader. I'm not quite sure what I'm supposed to say about carbon leader. I don't.
Yeah, and its origin.
Well, we're sitting there on an unconformity, carbon, conglomerate, quartzite, shale, which is the green leader there, and sometimes you get some of those missing, but that is the reef package. That carbon can be carbon seam, it can be fly speck carbon, can be little veinlets of carbon, depending where you are. And obviously it's got high gold. Now, I don't know, I'm not sure I want to sort of take it all that much further. I do not sort of support the idea that these are corduroy tables or fly speck carbon coming in from fertile granites, hags or whatever they were called. And I think most people have converged over the last few years that this is introduced as hydrocarbons after burial, and those are probably moved around a bit like hydrocarbons move around in oil fields. And of course, these are now Archean, so it's quite a lot different from something in the Mesozoic. So I'd see them as introduced after burial, and it's just my sort of preference, but I'd see them probably being pre-gold and a wonderful site to deposit gold through reduction, and a wonderful site to precipitate uranium through reduction. So you get your uraninite, and you actually do those quite separately. They don't have to be together. But as long as you can get the carbon in, you've got a great reductant to pull metals out of any fluids.
Okay.
I think there's another thing on the carbon leader, which people around the world forget, and that is how difficult it would be to drill a hole in the middle of Brazil or Canada or Australia and even recognise carbon leader. And I know that the drilling that would be done sort of Carltonville or somewhere, you know when it's coming up, you take special care of the core, all that sort of stuff, because you know how to treat and handle carbon leader. To hit a 1 or 2 centimetre seam and pay attention to it in the middle of Australia probably just wouldn't happen. I mean, I think we could drill through it, geologists on site. Yeah, I mean, something happened there, but and not realise that they'd gone through something like that. I just think it would be a very hard thing to find in a greenfields type project, or sorry, not find, to recognise.
Okay, George got an extension there, Neil. Obviously, the rhenium, osmium, datium, gold, and pyrite, and the support for a detrital origin.
I think take a look at the literature in that around 2000, 2004, there was a lot of fuss made about the rhenium osmium. It's gone right off the agenda, and I think that probably is best expressed that everyone recognises it's wrong. It's as simple as that. Probably oversold to conclude that gold was much older, and it just never hung together. So it's just one of those things that sort of could try at the time, but the science didn't really hang together. I think probably the 2006, it's an atmosphere GSA special publication. There's a section in there that Jonathan Law's written going through why it was a little bit superficial, and there's it doesn't really mean what perhaps it was initially thought to mean. Okay.
Interesting point. We see some similar analogies in the dating of diamonds, where you end up not having representative samples, and you sort of hang your hat on small diamonds and small inclusions, and then once you start looking much more extensively at a full range of diamonds, you start seeing a very different picture as well too. Just a broad analogy. Anyway, more questions, guys?
I think probably the rhenium osmium is perhaps a little like the hags and those things. They all, and the golden arc that Victoria's talked about, they're all interesting things to throw up. They're interesting things to test, and they need to be integrated with all the other information we've got, rather than just say, I've analysed a new isotope and I now have solved the whole VITS. I'm sorry, life just doesn't work like that.
No, I agree with you fully, Neil, and I think it's a lesson for all of us. I mean, if you see you know, see the tools available today and the work that's been done, and just, you know, the old TMS mountains here down in the Cape are a very good example. They used to be boring white rocks. Well, sure as hell they're not boring white rocks anymore. Yeah. And just, I mean, if you were an exploration man, I mean, what's big picture? I mean, this is aimed at people like you and Graham. You know, where would you go prospecting and looking for extensions of gold today? Is it all getting deeper? Are there areas that, and I think there are, probably answering my own question, you know, that should still be a target for companies?
There's possibly two. I think you're talking about in South Africa around the Witwatersrand itself.
Yes, yeah.
And I think there's two angles there that I'd pay a little bit of attention to. One is the one of where would you actually explore? And of course, I can't put a cross on the map and say one hole will find a new Wits for you there. And the other one is sort of how I'd handle the science and all these ideas, like be it alteration, be it this deformation, be it folds and so forth. I'd sort of tackle by supporting those in research and saying, I'm not sure I completely agree with you, but I think you should be backed for support to take that further, to see if it's right, to see if we can use it, to see if we can all understand it's better. Now, it might be alteration in this case, or maybe many other things, because we need to use these tools. And if you think of structure, I would guess during the era of vibrosize, a huge number of people could explain to the public or to their colleagues what vibrosize is about and how it works. At the same time, I doubt many could explain alteration that way. Why is it interesting? How do you pick it out? All that type of stuff. So there's an education side there to get confidence, and to me, that's part and parcel. As far as where, perhaps it's a little bit anecdotal, but I think I recall a vast amount in the companies, major companies, sort of databases, if you like, where I think there's lots and lots of intersections all over the place that just weren't put together or just didn't hang together and so forth. And maybe we start looking at things a little bit differently that way, perhaps in terms of some of the fluid channelways, learning a bit from Barberton, perhaps a bit from the alteration and so forth. But yeah, I mean, I sort of got a vague idea of how one would go about that. I don't have an instant answer that it's got to be X.
Question to Adrian. Adrian, where would you go exploring in the Wits today? Leading question. Would you spend your money there or not?
I think that's two questions. And I'm not going to answer the second one. Look, I think Neil's quite right. The archives, the core, the looking at all the exploration that was done by the majors between the major goldfields, and you know there was a spit here and a spat there, and everyone said, oh well, that's never going to be economic. It's at 1,500 meters or whatever. Yeah, go and look at that. So start your exploration in the archives and the core. However, whether you can get access to that and whether it's in a state where you can make sense of it, yeah, I'm not sure.
I think there's one or two things I found intriguing. One is chatting to Matt Mullins, and he always stressed about a shear zone running 25 grams that they were mining on Rand leases. Now, that's not another Driefontein, but it's going to be walked over, and I'm not quite sure where those things fit in. And I guess the other one that really caught my eye is on my visits to Velcom, particularly to talks that were dominated with the audience of Anglo, it was always, I think it was called Murphy's Law, where wherever it gets more structurally complex, we have to go there because the grade goes up. Now, yes, it might be Murphy's Law saying, well, I've got to mine in more complex things, but my God, that's Julian's thing all over. You need complexity, you need repetition, you need, and we saw it with Alex's thing and Caitlin's as well. So I wouldn't just dismiss that and say it's Murphy's Law. I'd say, well, hey, I think there's something in that structural complexity and good grades. But of course, that never gets recorded. So it would be hard to go and open a book and see what I'm talking about.
Graham, your comment on that?
Yeah, John, I think let's look at it this way. I think any development in mines will be brownfields. From my talk some 18 odd months ago, I would probably say really the Free State goldfields. The area north of Allen Ridge, very prospective, a lot of work done, a lot of data. As I think reasonably well understood, but let's look at it from a practical point of view. I don't think anyone is going to look at starting going in for a new mine there. Very deep, obviously the investment climate not that wonderful. There is a lot of data. Would be a good exercise to be sort of put together a rigorous system of sort of analysis, interpretation, could come up with some interesting ideas there. But just coming back to sort of the side of Neil's talk there, for those of us who worked north of Allen Ridge on Target Sun, the Dreyer's Kale, let's just call it the group, did yield some rather interesting rocks containing some interesting but some very anomalous gold concentration levels there, which when you think of the 80s and the 90s, the heyday of, let's just call it the sedimentological approach, that the gold settings there were totally at variance with what we were thinking of, there. And we never really understood it. When you've got gold sitting in polymictic diamectites, etc., that are diametrically opposed to the conventional model. Work needs to be done there. I think the Dreyer's Kale, the northern extension of the ubiquitous boulder beds in the southern Free State, I think there could be some interesting clues to the evolution of the Wits Basin, particularly the terminal phase. And as I recall from some work that was done, the upper Dreyer's Kale, immediately in the footwall of in some instances where the VCR was developed as well, and then with the overlying Clipperfiesberg lavas, there was reported that there was a significant carbonate alteration zone extending, I think, up to 20 meters below the top contact of the Dreyer's Kale. But as I say, no work's been done on it. The core's lying in Allen Ridge. It could be a very interesting academic project, perhaps even a PhD thesis level. But I think until it gets recognized and a research project is proposed, I think we'll never really know what happens in that terminal phase of the Wits Basin.
So final question to you, Graham. Are you a placer or non-placer theorist?
John, based on what I've seen up on the Dreyer's Kale, I'm very much a hydrothermalist there.
Okay. Interesting. Right. Other questions? Was everyone golded out?
I think that carbonate thing that Graham mentioned, putting that together, trying to understand what it's sitting there, would certainly be interesting. And there's a number of other interesting things that we don't quite know where they fit in, like a lot of Mike McQuarrie's things on Western Deep levels, the VCR there. VCR at Witwatersrand Cons is very unusual. I mean, it's running high grade. You have a look at it, and I just wonder whether it's not even quartz. Maybe it's an albite rock, but it's just not normal VCR as perhaps the old Anglo people would recognise it from Clarkstorp and Carltonville. So a lot of these differences here, we sort of need to pull together. And I can recall there was a VCR one-day symposium and other reefs one-day symposium. I just thought those were brilliant, where you just get a bunch of people and say, you and you and you all know we've got a bit of VCR, tell us about your bit of VCR. And you stand back and look and say, my stuff is not the same as his stuff, and so forth. You see the bigger picture.
Yeah, perhaps the last question, and you sort of started on exactly what I was going to ask, Neil, and for Graham and George Henry and the other people in this group who know the Wits well, know the Wits. I mean, where is the research being done today on this amazing gold deposit? I mean, is there any work of real consequence being done? I mean, surely this incredible basin has the most amazing and obviously largest gold resource, but has it now been sort of lost and forgotten? I mean, you, Neil, must be fairly up to speed on research in the Wits.
Well, thanks to some work that Caitlin's been doing, yes, and I think I can praise what she says, that the number of publications on the Wits has fallen dramatically from 1980s and 90s, and then perhaps the last 10 or 15 years. And I think that it's hard to know what that reflects. It's either that people don't work on those things like, say, rhenium osmium, because it's not taking them where they want to go, so they go to some other place around the world, or it might be access, or it might be funding, or it simply might be there's an accepted story, perhaps, that is what it should be, and it's not really coming out and working out that way. So there's a lot of reasons why the research won't be done, but I don't think it's a case of guessing what the answer is, whether it's alteration or not, or structure or not. It's more a case of saying, I'm going to line up a bunch of good people and you go and find out what you can, and we'll sort of argue later what you're coming up with, but we're not going to decide beforehand that this is what we're going to fund and this is what we're not going to fund.
Mm. Yeah, and I mean, importantly, from an economic and even economic development and job creation point of view, I mean that's the sort of where your research has always been aimed, Neil. Are there more economic deposits that could be developed? And it, for me, it's a sad reflection on our industry and our science that I don't see any real modern. I mean, we've just seen this amazing work being done on Barberton, but I don't see that happening in the Wits. I'm happy to be proved wrong. Graham, last comment, or Adrian.
Well, Johnny, I think the work's not being done in the Wits because people just think, well, it's going to have to be 2,000 meters deep, and it's just going to be, the capital is too much. I don't think people think there's anything big enough at that sort of depth to warrant the economic side, where Barberton or the Murchison, you can still get in there and do that. But it's quite sad that after more than 100 years, we would still have a discussion or an argument about the origin of the gold. I mean, if we did a straw poll now and asked everybody, put your hands up if you think it's all hydrothermal, or put your hands up if you think it's all placer, you'd probably get, I don't know, 30% each side. And the other 40% would say, well, it's a mixture of the two, of course. And that's more than 100 years, and we're not really that sure of it.
Mm. Yeah. Interesting point. Graham, last comment.
John, I think from the academic point of view, I think interest has been lost. I mean, we did have the heyday of Wits, exploration, Wits, academic work, basically 80s, 90s, but I don't think much, very little has been published. As for Anglo Gold, as part of their departure, has opened up their vast database for people to look at. If other companies could take the data, I'm thinking of Harmony with Target Sun, and open it up, there could be some interesting research done there. But again, I think there's just basically no real interest in the Wits, because everyone sees it as a declining industry, a declining mining sector.
Yeah, fair comment. Okay, in the absence of any more questions and discussion, thanks Neil, thanks Alex. I think Caitlin's on. Thanks Caitlin. We really enjoyed all these talks, and we look forward to another session sometime in the not too distant future, presumably Geocongress, which is I think going to be in early 2023 in Stellenbosch. You know, there will be some gold presentations. I think Neil, you say you're planning on coming, and I guess Alex is there, and Caitlin's just down the road. So maybe we look forward to some more work next year. But thanks very much. It was tremendous. Henny, do you want to sort of finish up on various admin and bits and pieces?
John, you just give us a bit of info on the 7th.
Yeah.
Then I think we can close with that.
Okay. I think everyone may be aware, or if you're not aware, next week the GSSA are running a series of activities, presentations, field trips on geoheritage. I think it starts off on Sunday with Richard Viljoen and group in the Botanical Gardens on the West Rand, doing I think both, it'll be streamed, a presentation really an acknowledgement and in memorial of his brother Morris, and there's been some interesting new work and upgrading of the sort of rock garden in the Botanical Garden. And then there are a number of, I think sort of Monday or Tuesday, Wednesday, Thursday, there are various presentations highlighting some of our museums. And on Thursday, the sort of Overberg group will be giving a series of presentations in the morning about geology and work going on around here on geoheritage. And then anyone in the area at 2 o'clock next Thursday, we're going to meet in the Harold Porter Gardens at Betty's Bay and do a field trip there. There's some fun geology and a lovely rock garden that we're busy upgrading in Harold Porter, and then go across to Betty's Bay Beach, the West Beach, where there's an old Second World War radar station and some wonderful exposure of the tillites, the puckates, and sandstone dikes in those tillites from about 444 million years ago. The most welcome, and for those of you who don't necessarily get GSSA flyers or newsletters, if you just go to their website and look at GSSA and geoheritage, the program for next week's activities will come up there, and it's a link to all the activities that are taking place. So that's my input for the day. Thanks everyone. Thanks Henny, and we'll see you again next week and then in the weeks to come. So and then going forward after or once we get into April, we'll get back to sort of a series of varied presentations, and then in the latter part of June we'll go into a diamond short course, online diamond short course with some mine and field trips in July. So watch the space, or watch Henny's space. Thanks Henny. Thanks everyone.
Okay, and as a parting shot, Mark Goodhart says if you guys want to read up a little bit more on the 1992 book by Minter et al. That says a close look at the Witwatersrand gold part 1, the morphology of gold micronuggets extracted from the Witwatersrand basal placer. So there's some reading for you guys in the text there, and after next week we will have some a nice relaxed look at all the mountain passes, part 2 of the Western Cape. Goodbye everybody.
Thanks Neil. Thanks everyone.
Thanks
all.
John. Thanks Annie.